Start our last session of the day, embodied carbon and how to eliminate it. And we have three absolutely amazing speakers in this session. And I will not read the slide out because I trust you can all read. So I would like to invite Jamie. Each speaker will have about 20 minutes of time to present and answer some questions. So I will be maybe looking at you to finish a bit earlier if I see that there are a lot of keen faces in the audience. So Jamie, if you please come and present, the floor is yours.
Moving backwards and forwards, that's nice.
You can do that, or you can do this. Just click on that. With the, yeah. There we go.
Lovely. Thank you very much. Good afternoon, everybody. It's really nice to be here. As mentioned, my name is Jamie Pitcairn. I'm a Technical Director for Sustainability and Circular Economy within Ricardo Energy and Environment. And been with the company for 20 years, and predominantly through that time been helping businesses understand carbon emissions, scope 1, 2, 3 emissions, and develop pathways to reduce those emissions. So what I'll talk about today is just a little bit of thinking around embodied emissions and the importance of embodied emissions, and importantly how to try and identify what methodologies we use to identify those emission hotspots and developing pathways to address those emissions. So yeah, in terms of scope 3, I mean, it's becoming pretty well understood now in terms of scope 1, 2 and 3 emissions. Scope 1 and 2 are your direct emissions for your organisation. Scope 2 are those indirect emissions that are expended on your part. And then scope 3 is the big bit that most people forget about, but it's a really important bit. And you'll see that there's generally 15 categories in the two loops at the below here. You have the upstream categories, which are those goods and services that you can procure, the waste that's produced, and any transportation involved in those raw materials or components. And then you have the downstream, and effectively that's the big part there are the in-use of your products, and that is where it catches a lot of businesses out, because if you're responsible not just for the production of that product, but you're also then responsible for the emissions associated with that product, that's where you can start to hit significant issues when measuring your scope 3. I think the point here is that it's not just sufficient nowadays just to look at your scope 1 and 2 emissions. If we're going to really tackle climate change, organisations need to be looking at scopes 1, 2 and 3, and they need to be doing that to get a fuller picture of where the impacts are across their operations, but also across their products. So why are scope 3 emissions important? And what I thought I would do is actually just go up a little level. We've got COP coming to Glasgow next month. So rather than just really looking at the business level or looking at the product level, just to have a look at the country level as well, because we need to look at emissions at the country level if we are going to start to deliver against COP commitments. So there's the various definitions in terms of different emissions. So we've got territorial or production emissions, and this is the emissions that's associated with the activities within UK border. So that's why it's territorial emissions. And that footprint is calculated every year. It's actually Ricardo that do that, and we've done it for a good number of years now. So we will be able to calculate the scope 1, 2 emissions for the UK, and that's what we report up to the UN as part of the UK's requirements. But then we have these embodied emissions, and these are the greenhouse gas emissions that go beyond just what's done in your borders, and these could be the mining, extraction, the transport, the manufacturing processes of these products. So effectively that's us looking more at the scope 3. And if you come back down into the UK level, we have the UK consumption emissions, and these are the emissions that's looked at the consumption of the goods and materials that we use within the UK. So if we import a train, if we import a car, a television, it's all of those embodied emissions associated with those products. And if we look at the UK as a whole, we're roughly 1.1% of global greenhouse gas emissions, which for a small country like the UK, that's relatively high. But if you actually look at the manufacturing emissions within the UK, we are offshoring nearly 90% of those emissions. So we're consuming a lot of materials that we're not actually including within our carbon footprint. And that's the big issue with Scope 3 emissions. If we're truly going to tackle greenhouse gas emissions, we need to be looking at these embodied emissions. And if we start to look at the UK from its consumption based of manufacturing sector, then you're nearly 50%, so nearly half of the emissions at the UK level would be attributed to manufacturing. So you can start to see how we're going from maybe 10% of our production-based inventory to nearly half of the emissions coming when we're starting to look at embodied emissions. So that's why embodied emissions are really important. It gives you that fuller picture. And the manufacturing sector is really important as well. You know, we've got the rail sector involved in this event today. So a large manufacturing sector, both in the UK but also overseas as well. And for the transition to net zero, we're going to need decarbonised transport. We're going to need clean energy. We're going to need sustainable buildings and sustainable products. So it's really important that if we are to become a sustainable nation, we need to be looking at Scope 3 emissions, not just the Scope 1 and the Scope 2. And really the recognised way of looking at Scope 3, or at least emissions across the whole value chain, is through lifecycle assessment. And if you look at life cycle of the manufacturing process, you can look at the raw materials, you look at the energy, and you look at the water inputs into that manufacturing process. So that's just one little part of the value chain that needs to be looked at when understanding emissions for a product or a service. We need to look at the components that go into the manufacturing process. We need to look at distribution. We need to look at the use and the end of life of these materials. And in the earlier slide, I had a little pie chart, and I should have mentioned it then, but Ricardo's emissions, and we're a consultancy with a little bit of manufacturing, our Scope 3 emissions is 96% of our overall footprint. And when we first calculated that, we sort of picked a chin up off the floor and sort of thought, well, why is this? And the reason is that that little bit of manufacturing we have is, well, not just, but the big part of that is engines for McLaren, the precision engineering division that produces really high performance engines. And not only are we responsible for the materials that go into the manufacture of that engine, are we responsible for the emissions in producing that engine, we're also responsible for the emissions of the in-use of that engine, for the whole life of that engine. So that's a big hit. So any manufacturing business now, when you start to look at Scope 3 emissions, it's a significant issue for these businesses. And at the minute, it's not mandatory to report in Scope 3 unless you're trying to follow the Science-Based Targets commitment, in which case if your Scope 3 is about 40% of emissions, then you have to include it in your carbon footprint. The direction of travel is you will start having to report on your Scope 3 emissions. So it's really important that you understand these Scope 3 emissions, and that's where the life cycle assessment methodology can help you, because it helps you look across your whole supply chain in terms of where those emissions are. And importantly, it allows you to understand a really important aspect of your Scope 3, and data is a big issue in Scope 3 because LCA gives you access to that data and that insight. And generally what will happen is that businesses will start to use spend data. So if you're procuring goods and services, you understand how much money you spend procuring a good or a service from a certain sector, and there will be emissions associated with that sector. And that allows you to give you a high level view of the emissions associated with your spend. Heavily modelled data, heavily inaccurate, average, and so not very helpful when you're trying to make decisions around where you're spending on goods and services. So life cycle assessment allows you to do a much deeper dive into those different categories and understand where the hotspots are through your spend of goods and services, and also where your impacts are from the in-use or end-of-life phase of those products. Because you've got that value now from life cycle assessment, it's much easier to start to produce, more a sort of a low carbon trajectory for your Scope 3 emissions. And this is the same approach you would use for your Scope 1 and 2, but it's much easier to get energy consumption data because you just read your bill. But when you're looking at your products and your components and materials, it's much more difficult. So life cycle assessment allows you to do that. And if you don't have that level of granularity, you're not able to understand where you can act as a business, and whether that could be from procurement processes, what materials you're specifying, what components you're buying, down to product design. So how could you redesign certain components of your products to help you with the in-use phase or the end-of-life phase of those products? You need that level of detail to understand what your mitigation measures can be as you start to plot that sort of trajectory towards net zero. And just to bring that to life a little bit, a couple of examples from the rail sector. We do a lot of LCA work at the minute, because if you want to look at Scope 3 or look at sustainable products in any detail, you really need to be conducting some LCA work. So this was 5-6 years ago, something that was growing quite nicely as a consultancy, sort of offering within the business, and now it's just growing exponentially, because if you're a manufacturing business, if you're a producer of a goods and service, and your client asks you for that information, you'll have to go and do a life cycle assessment. And to give an example, we are doing life cycle assessments from individual products, bricks, pieces of concrete, cement, all the way up to nuclear power station. And we've done 3 nuclear power stations in the last year. We do airplanes, all components of these products, and really a nuclear power station is just a product. It's just a very big, complicated one. So this was an example from a client that commissioned Ricardo to do some work, because when it was bidding for HS2 work, and as part of that, they had to calculate the carbon intensity of that train per passenger per kilometre. So we worked with them, we got the bill of materials, as I was saying, it's every component, every material. You can provide a huge inventory of all of those materials. You look at the end of the life of all of those materials, what's recyclable, what's not, what's reusable, what's refurbishable. You factor in some assumptions around the end of life of them, and you still get the big bit in the middle, which is the in-use of that train. So we worked very closely with the manufacturer and came up with a model that would allow us to look at the in-use emissions of that train. And what was interesting is when you go into a good level of detail as part of that, it's not just the train going from A to B and the number of passengers it's carrying. It's the sub-components of the train that's quite interesting. So where are the emissions associated with the domestic functions in a train? The heating, the cooling, the HVAC, the catering systems, the weight of all of these different components, the weights of the chairs, the carpets, the materials. That's when it gets quite interesting, when you're looking at all these different individual components. At that level of detail, you can then start to make some informed decisions about what may help you reduce your carbon emissions. And at the end of this study, we created a very nice calculator that allowed them to model different scenarios, and was able to submit the train with their bid with a calculator that allowed them to look at estimated emissions, per gram of CO2 per kilometre per passenger. And I think Joe isn't here from Network Rail. I don't know if anybody else is from Network Rail, but it's interesting that Network Rail have just done a net zero strategy. They've looked at their Scope 3 emissions. I've had a look at that, and from their goods and services, from their Scope 3, it's something like Scope 3 emissions are the high 90s, 95%. Sorry? 96. Whew, wasn't too far off. 96%, it's a big issue for an organisation like Network Rail. And if you look at the supply chain, there are 5 key categories, looking at civils, buildings, electric, signalling, etc. track. From that, I could expect that some of the big materials are in construction, building supplies, steel, energy generation, etc. So that's where some of the decisions have to be made. How can you take carbon out of some of those categories? And a nice little example that we did was for a client that makes troughs, cable troughs for the rail sector out of recycled plastic. And what it's compared to is against a conventional concrete block. And they wanted to compare the sustainability of the recycled trough versus a more conventional concrete block. And I think the challenge there is that the concrete block is generally cheaper. So for procurement processes, it's difficult to compete when you've got a cheaper product. So they have to really put a lot of weight onto the sustainability of that product to be comparable. So that's why they were employing ourselves to do that. So again, we've similar process. We conducted a comparative life cycle assessment, studying alternatives of the concrete versus the recycled product. We looked at the full process, from scrapping of cars, getting the plastic, the processing, refining of the plastic, the moulding, the whole process, built the 2 comparative models, and at the end, pleased for them. We're always very impartial in these exercises, but for them it was a very positive result, with that recycled trough being 4 times, or proper terminology is, has a smaller footprint, if you like, or global warming potential than the concrete component. So a couple of examples there of how we're seeing more and more life cycle assessment being deployed to try and help businesses understand the impacts of the products from the manufacturing process through in life through to end of life. And just to summarise really, that we have to start thinking about the actual overall emissions of our products and services to take full account of where the true carbon emissions are. It's really important, otherwise we'll be making really blinkered decisions and not looking at the bigger picture. We have to look upstream and downstream. It's not just important looking left or right or just focusing on your scope 1 and 2 emissions of the manufacturing process. We have to look at the whole picture. And LCA is a really good tool to help you do that. You can tailor the tool in terms of what assessments, what impacts you want out of that, whether it's just carbon, whether it's global warming potential, whether it's ecotoxicity, biodiversity impacts, but it does allow you to look across that value chain and understand the sustainability of your product. So I think it's an interesting dimension for the rail sector. I think it's a tool that the rail sector will be using more and more, either through procurements, or you'll start to see individual operators in different parts of the supply chain beginning to create a bit of a differentiator from the competition, and that's something we're seeing already, is that people are trying to get an early march in the way they're designing the propulsion systems, but also the rolling stock themselves. And that's me. Time okay?
Thank you very much.
Thank you.
So if you could just, do we have any questions from the audience?
20 minutes was up.
Oh. If you don't have any questions, that is also okay. I'll just adjust a bit of a mood lighting here. Okay.
Yeah.
Yeah. Okay, just checking the setups. Right, you've got a question.
Hi, I'm Eggleston from Edinburgh. You mentioned about McLaren and the emissions associated with the tailpipe emissions. I think you mentioned about Ricardo also being associated with those,
yeah,
and that's being part of Scope 3. How does that, because with McLaren, would they be reporting the Scope 1 for those emissions? And therefore, how would that work in terms of reporting under legislation like SSCR?
Yeah, it gets really difficult when you're looking at boundaries of this, but essentially we're making engine. It's the engine that creates the emissions, not the car, if you like. So we get, and it's boundaries, so you create boundaries when McLaren's doing it, and that sits in our boundary, unfortunately. So it gets quite complicated. I think this is something that will evolve in future, because I think if you looked at all scope 1, 2 and 3 emissions for all businesses, it will be more than all emissions in the globe, so there will have to be some refining. I think the point now is that we just have to mature the science and mature the process and understand the boundaries. And when you're looking at supply chains, what's happening now is that you'll have suppliers who are supplying to 3 or 4 different OEMs or top tier manufacturers, and you're having to do some proportion. So what proportion of your sales are attributed to that business? And that's how you start to wrap the boundary around it. But it's certainly not an exact science, but it's more around the responsibility of that product. So if you're just doing a component on an engine, on a wing mirror or something, then you're not really responsible for the emissions of that car, because really you're just being moved around. But you will have a proportion of the weight of a mirror eventually will come into some of the overall emissions. So that's why all the OEMs are very, very busy trying to take weight out of cars and trying to take carbon out of cars. Yeah, no, that's a good question. Thank you.
Okay. Thank you very much. If we don't have any more speakers, now you can applaud our speaker. Thank you very much. It is on. Okay, so now I would like to invite Victoria from Arcadis. Victoria, the floor is yours. So you could just click on that and it will progress to the next slide.
Thank you very much. Good afternoon, hello. I hope you're all still awake. I'll try and keep it as interesting as I can. So I'm Victoria Eggleston. I work as part of the bridge engineering team in Arcadis' York Rail office. And I recently undertook in the last year or so a role as the carbon champion of the office, which basically I'm here to highlight improvement areas within the business. And I also produce and review all of our embodied carbon reports that we send out for all of our projects for different grip stages to all of our clients. So I'd quite like to start by highlighting that I myself, my team and Arcadis are by no means experts in embodied carbon. I'm not sure anybody in 2021 at this stage can actually claim that title. We're just trying to do the best we can with our projects at the moment and to sort of make our designs as efficient and low in embodied carbon as we possibly can. So today I'm going to take the opportunity to run through exactly what embodied carbon is and what Arcadis is doing to reduce it as best we can and reduce it through our designs. It's quite interesting from being here today and looking at all of the presentations that we've had. We're talking about the future. My presentation is not as elaborate or large scale as the ones we've seen before, but it's the small steps that we can all make that we're starting to do today and over the last couple of months that at least it shows we're starting to make a progression. So what is embodied carbon? This is the woolly bit. So embodied carbon considers the amount of greenhouse gas emissions that are released throughout a production supply chain to produce a material or a product. It considers all the extraction, transport, processing and fabrication activities, and it differs from operational carbon, which was covered very well earlier today, so I won't go into detail, but that normally relates to the heating, cooling, powering and operational phases of the structure. So are we talking about just carbon? To calculate the embodied carbon, a standard unit of measurement is used, which is a carbon dioxide equivalent value. And this carbon dioxide equivalent enables different greenhouse gases to be expressed as one single value. And all outcomes are then standardised against a global warming potential for 1 kilogram of CO2. And this is invaluable for us when we're looking back at designs and trying to make comparisons and refine all of our material choices, because you can compare them all against each other. So why do we need to calculate it? As you can see from the pie chart on the screen, the construction industry alone is responsible for 39% of energy-related carbon dioxide emissions. And the second graph shows the breakdown of the whole life carbon footprints into embodied carbon and in-use CO2. As an industry, we're getting much better at reducing in-use CO2, but as you can see from the graph, the majority of carbon footprints are now made up from embodied carbon within the asset. And the prediction for the year 2030 is still following this trend. So reducing the embodied carbon for such a huge industry can seem like quite an overwhelming task, and myself included, and everybody could be forgiven for saying, where do you even start? And we've had some great examples of where we go in the future, but what do we do now? So we at Arcadis have tried to simplify that as best we can. So to start with, we needed data, as I'm sure you've all heard and will agree with me, that what gets measured gets improved. So we started collecting data about 2 years ago, and all of our embedded carbon values for all the projects and different materials that we've started using. And we're trying to identify specific bridge types and materials which were highlighted as our problem areas. So how do we calculate it? The Bath Inventory of Carbon and Energy database, we're up to version 3 now, is the world's leading source of embodied carbon energy and data. This inventory contains all predefined embodied carbon conversion terms in terms of that CO2 equivalent that I mentioned before. All of the factors are given in kilograms of CO2 equivalent per kilogram. So the only calculation we have to do, in addition to all the existing ones we already are doing as part of the design, is calculate the mass in kilograms of each material used within the project. This is then multiplied by the conversion factor that we get from the inventory to produce an embodied carbon value. Now, these calculations can be done by hand, and they can also be done on an Excel spreadsheet or any method you choose. But we like to use the RSSB RailDecarb tool, which is an online version of the inventory. And the tool's a great way for you to store all your products and share it with different companies and colleagues. And it's a great way to refer back, and you can extract different and compare different projects to the other. So what is Arcadis doing? So as of the 4th of September 2021, all teams working on Network Rail projects are to comply with the new sustainability requirements, which basically means a formal capital carbon assessment is now required as an absolute minimum on all development works that meet both the following criteria. So a project value greater than $1 million, or a project that's encompassing tracks, structures, earthworks, electrification, and fixed plant infrastructure or buildings. So as I mentioned before, we began collecting the data for all of our projects at various different grip and pace stages, and we highlighted the specific materials where we could begin to make savings. And the key hotspot materials, unsurprisingly, included concrete, steel, fill, and GRP. So these were all the biggest embodied carbon contributors, and reviewing how we specify and design these elements and how we propose material uses with thicknesses will all have an impact. So your next question is probably going to be, how are we doing it? So once the problem areas were highlighted, we began discussing what we as designers can do to improve them. We could reuse existing materials or even structures where we can, which means potentially opting for strengthening works over complete reconstructions or using demolition waste as backfill for new structures. We've looked into specifying lower carbon concrete mixes, so that we found out through looking at the inventory that the higher the strength class, the greater the embodied carbon factor. So this is a very quick and easy win for us because, as you can imagine, we use a lot of concrete. So we're starting to limit the specification of carbon intensive materials, and we're recommending lower carbon alternatives, which include highly recycled content materials. But most importantly, we're trying to maximise the structural efficiency of our designs, because that's what we as engineers can contribute the most towards this embodied carbon journey. So, some examples of carbon reduction. We have been reducing the concrete grade from sill units from C5060 to C4050. We've been reducing the thicknesses of steel elements and plates, and I've got an example on the next page to show you when we did that. We're reducing the required strengthening works and the fill materials that we use. And again, probably above all, we're trying to share knowledge between our teams so that the next time we pick up the same design, we can implement it and it's almost standard procedure. This is going to try and be my Blue Peter moment of here's one I did earlier. The intersection bridge was a relatively small project, and you can see we're basically reconstructing one span of an existing 3-span bridge. So in terms of projects, this was quite small, and only the one span was failing its assessment. So for this project, it wasn't possible for us to strengthen the existing span. Therefore, a reconstruction option was the only option. And it was decided that at option stage, that a billet deck was the most preferred method of reconstruction, which I'd just like to highlight is most certainly not the most carbon efficient design we could have gone with. But we as designers can do the most, we can provide the information, but at the end of the day, it's the client who chooses what they want for various different reasons. But it's our job as the designer to then take that design that they've chosen and maximise its efficiency and use the most reduced carbon materials that we possibly can. So the team sat down and refined the design to allow for an 100mm thick steel deck plate instead of the usual 125mm, which is usually used by ensuring the deck plate is fully utilised. So we had a 25mm thickness saving that was created over the deck area of approximately 78 metres squared. So this is, again, just to emphasise, this is quite a small area that we're using this on. But even alone, this resulted in a weight saving of 15,443 kilograms, which you can imagine also has safety and cost benefits if you don't need to hire cranes that are, lower capacity, and we're transporting it, it's much lighter, and it wasn't just the carbon saving we got there. And we also got an embodied carbon saving of 50,497 kilograms of CO2 equivalent. So that's great. We made the saving, and you probably sat there thinking, well, what does that actually mean? So, to put into context, 50,497 kilograms of CO2 is equal to the greenhouse gas emissions of 11 passenger vehicles driven for a year, or 126,909 miles driven by the average passenger vehicle, or the equivalent CO2 emissions for nearly 500 gallons of diesel consumed, or 6.1 homes energy usage for a year. So, where do we go from here? That's fine. So, the things we can do to get going, so to change the attitude towards sustainability, I'm sure we've all been in a meeting and we tend to find the things that drive it are cost and programme, and health and safety and everything else. So sustainability is usually the last thing on the agenda. It's the thing that gets cut when meetings run forward. We need to sort of change that attitude and insist that it is part of a conversation. We need to consider our material use for new work and record and analyse our data on a project by project basis and add it to a value log that we can keep referring back to. We need to set ourselves targets and monitor our progress against them. We need to use local material suppliers wherever possible, and also share examples and information exactly like we're doing today. We need to challenge and encourage our clients. It's time for us to open up a conversation with our colleagues, our clients and our contractors about what they are doing to reduce embodied carbon and what Arcadis as a business can do to support them. We need to include contractors in the early stages of our projects to ask for their input on lower carbon construction techniques or material suppliers. So for example, with the core 6 intersection bridge that I just showed you, it was too late. By the time we found out how they were going to construct it, I did a carbon analysis of the materials, but then also a separate one for the plant and transport of how we were going to build it. This was a 2-day blockade that they were building this bridge in, so it's not a very large construction at all. And the embodied carbon that came from the plant and transport equated to just under what half the entire material would be for that entire life cycle. So for 2 days, you've almost cancelled out any helpful reduction you've made in materials. Now, that's not us as designers' job to do that, but we can encourage the conversation to ask what they're doing and start to challenge them because they have more of an input than I think they expect. So as a business, we need to continue to make these small changes. And as design engineers, we have a responsibility to refine our designs and strive for continual improvement. It's about maximising the efficiency of designs and ensuring we make the most of the materials and construction methods that we choose to use. It's the small and continual changes made, like the example that I've just shown you, that are going to make the biggest difference. And if we continue to refine the designs and challenge our colleagues and clients, you can imagine the impact they'd start to have over time. Thank you.
Thank you very much. Do we have any questions? Over there. I'm coming. Give the microphone if you can just reintroduce yourself.
Hiya, Wendy Whelan at RailDecarb. I'm sorry, it's not a question, it's more a comment, but as one of the people who fought really hard to get that mandate requirement into our contracts, it's just really looking to see our suppliers embracing it and working with it and doing what we need them to do. So
Absolutely, thank you.
I've raised there. There we go. And one more question here. So, same rules apply. I'm well running. Quick transaction.
Thomas and WSP. I applaud your efforts on the intersection bridge, Victoria. I think it was great you showed the savings in embodied carbon, but I can't help thinking from a railway perspective, you missed a big trick in that, which was to abandon the concrete sleepers and the 250 mil ballast depth and go with a steel sleeper with a 150 ballast depth, which would have saved carbon in the depth of ballast, carbon in the concrete sleeper, and would have provided double the savings that you actually achieved. Did you consider at any stage challenging the track form on that bridge?
So we absolutely did. We struggled a little bit with it being one of I'll go back to the page. So with us only reconstructing one of the spans, we couldn't do much with the track alignment because it had to run smoothly over all three of the existing spans. So we couldn't alter the ballast depth or anything. We did consider using lower embodied carbon sleepers, but there was nothing wrong with the condition of the sleepers that were already there. So we actually, on this, other than a few spot replacements of the sleepers that were slightly wear and tear, we reused the entire system. So it was considered. There were many various reasons why we ended up going with sort of the design we did, but the billet deck steel reduction was by far the biggest thing we could do to reduce the embodied carbon within the designs. I'm sure I'm not standing here holding my hands up saying we sort of explored all of them, and I'm sure there are plenty of suggestions that we could go for in the future, which would be interesting. But yeah, we highlighted where we could use or save the most carbon in this, and the steel was the clear winner with having such a high embodied carbon.
Would you like to add something?
So that resistance you had to changing the track form, did that come from the regional engineer track, or where was the resistance? Where do you have to take the conversation to in the future?
It wasn't a resistance, it was more just to do with, we had a 2-day blockade to do this design. We were going to lift and reconstruct and align the whole track. That was a much bigger project than what we'd budgeted for than we had time to do in the programme, and with us only having such a small amount of time to actually, you know, have the isolations over to reconstruct it, it wasn't feasible for this design. I'm not saying in future it won't be. So.
Okay, so we have time for one more question. Well, in that case, can I ask you to thank our speaker? Thank you very much. And now on to the last speaker. Oh, it was already there. Apologies. There we go. Dr. Saran, the floor is yours. And you can.
Hi everyone. So I'm Saran Sohi, and I'm representing quite a large group, in fact a consortium of people working on this particular project, integration of greenhouse gas removal technologies into linear infrastructure projects. I have to say we're working mainly in the context of roads, but that wasn't necessarily the intention at the beginning. It's just a direction in which the current project has gone. But in considering these technologies, we'd like to think about how, beyond the current work, this may also inform and address other construction. So the lead partner in this consortium is actually Arup. Costain are an industry partner, and then I and my colleague Felix are the, if you like, the academic contribution from the University of Edinburgh, and we also work with colleagues at Newcastle University. So I'm an academic working in an industry-led forum, which is interesting, and it's actually been a good positive experience and lots learned, I think. In terms of this talk, I want to divide it into 4 parts really. The introduction, the project itself, so that's really the context where the project came from, the project itself, the current project, and then the technical feasibility of these technologies that we're working with, and then to identify or potentially identify opportunities within rail. So the introduction then. So we're working with funding from UK government for greenhouse gas removal. So this isn't really emissions reduction, it's about removing greenhouse gases, and more specifically carbon dioxide, in a way that offsets residual emissions. We are funded by BEIS, so the government Department for Enterprise and Industrial Strategy, and it's around £70 million at the moment, invested partly in 24 feasibility projects for different removal technologies. We're working with one of these projects, and then maybe 4 or 5 of these will, from 4 or 5 of these pilot projects will emerge beginning next year and run for 3 years. That's £70 million. In parallel, there's research-focused work through demonstrator projects, which is about £30 million. So anyway, this is quite a big investment at UK government level, at least relative to other countries worldwide. So the UK is setting a bit of a lead, I think, and I think COP26. I think it's an interesting time to be working on these technologies. I think I might have made the mistake of Googling ICE and jumping to the conclusion that these data were from the Institute of Civil Engineers. Now I'm wondering, based on the previous talk, whether it was actually the inventory for carbon and energy. But anyway, carbon and infrastructure. I think we've already touched on this point that, you know, a lot of the emissions associated with infrastructure aren't in the construction of the infrastructure, but in the use of that infrastructure. And I think it's an interesting question when we think about scope 1, 2 and scope 3 emissions in the context of construction. What we're really addressing in this particular work are the emissions embodied in the construction of the infrastructure. I think with roads, I think it's going to be interesting as we move towards electric vehicles increasingly, and the emissions of usage change. You know, whether or not that actually increases the focus on the embodied emissions of construction. In general, so if we think about the global situation with greenhouse gases and the need to remove greenhouse gases from the atmosphere at the same time as driving down emissions, I think we can then sort of use that way of looking at the global issue with climate change, specifically in the context of infrastructure. So the point is that we can do what we can to drive down emissions, and it gets harder, of course, as you do that. Each additional removal of reduction of emissions becomes harder and harder, more costly, and it takes longer to introduce the technologies that are required. So it's recognised, I think, that we're going to need to draw quite heavily on carbon dioxide removal technologies, CDR, in the coming decades to meet net zero commitments. So, I mean, the different pathways we might imagine our emissions reduction proceeding along, and that would then change the extent to which we depend on removal technologies. But even the most optimistic one, P1 on the left, would assume that we're going to use agriculture and land use change positively, that's AFOLU, to start removing carbon from the atmosphere rather than land use change contributing to the issue with increasing CO2 in the air. But in the less optimistic scenario in P4, we're really going to depend an awful lot on removal technologies to meet net zero, because emissions reduction is going to proceed slower than we might like. So at the moment, we sort of assume that we're going to rely heavily on BECCS, so bioenergy, carbon capture and storage, as our lead measure to achieve that removal. However, there are other options, and these are the ones that are being explored in the current funding from BEIS. So these are the more speculative options identified by the Committee on Climate Change. So afforestation, habitat restoration, and soil carbon sequestration. This is really about using land, but using land in a better way, if you like, in a way that tends to increase the amount of carbon that's stored in the land. But using fairly conventional interventions, just doing land management better, and sort of, I suppose, analogous to that, also building better, so prioritising wood over concrete and so on. But actually, the context of this talk is around biochar enhanced weathering. These are measures which haven't really been discussed a lot, but actually offer a greater potential per unit of material than some of the others. And I think in terms of permanence and efficiency, they are, I think, increasingly recognised as valid options. So in terms of the objectives of the current project, which I sort of implied or said is at the feasibility stage, it's about really establishing the scientific basis and the engineering considerations related to deployment of these GGR, greenhouse gas removal measures, biochar and enhanced mineral weathering, let's say EMW. And then as this draws to a close at the end of this year, really what is submitted to BEIS is the proposal for a pilot project. So we're at this approaching this point now where there's a detailed design emerging for a pilot project. And this would then be taken forward next year for 3 years with quite specific requirements in terms of carbon removal, but also a vision for how that will then propagate within the economy and deliver 1 million tonnes of CO2 removal per year by 2050. So that's be sort of a roadmap or a pathway to this larger scale impact. I've already outlined who's involved in the project. Maybe this just emphasises the structure. Felix and Abby are really the full-time members of this team. My own background is as an environmental scientist working mainly with land and soil, but particularly around carbon cycling. So in this current project, we're looking at we're looking at these two technologies, biochar and mineral weathering, think about how they may be integrated into the design of linear infrastructure. And I've already said we've focused on roads, or will come to focus on roads. In terms of the technologies themselves, they're quite different, but they're complementary in the sense that they can both be designed into the infrastructure itself. And I think our objective is really to offset, to remove about 10% or up to 100% of the embedded emissions associated with infrastructure creation. So these technologies work in quite different ways. The biochar is taking carbon that would ordinarily return to the atmosphere and stabilising it through a thermal process. It's about stabilisation of biomass to create a permanent store of carbon that is integrated into the land around infrastructure. So you've created a removal that is present in the infrastructure and can be measured and monitored and so on. Now, if you create a ton of biochar from probably about 3 tonnes of biomass, you remove the equivalent of 2.5 tonnes of CO2 from the atmosphere. We've given some examples of what biochar might look like. I mean, it's essentially charcoal, because when you thermally stabilise biomass, you get charcoal. Now, it is combustible, so if you ignite it, it will burn away and go back to the atmosphere. But in terms of efficiency of stabilisation and the permanence, the heating of biomass is a very effective way of achieving it. Mineral weathering is a very different proposition. This is about creating material within infrastructure that undertakes the removal once it's been deployed. So what you put into the infrastructure design are mineral fines, and specific minerals, and particularly dolerite. And during the weathering of that material, you create CO2 removal, because the weathering products of dolerite react with CO2 that's dissolved in the water, soil water essentially, to either precipitate mineral carbonate within the soil, or generate stable bicarbonate ions. That bit's sort of dropped off the bottom there of that paragraph. So it's stable bicarbonate ions. Once those are in dissolved water, they will be exported from the site, so they're not going to be measurable on the site, but they are going to have gone somewhere where they're permanently stored. So in one of these technologies, you are creating the storage at the point of deployment, and the other you're deploying the potential for a removal of CO2. So these have implications in terms of the timeline for the removal and the ability to the time frame over which CO2 can be claimed. CO2 removal can be claimed. The amount of CO2 that's removed by minerals is less per tonne than it is for biochar. So that's also different, as well as the timeline. But the cost is also different. So dolerite, when we look at there's a large cost range here. So for biochar, somewhere between 12 and 120 pounds of per tonne of CO2 removed. It's a very wide range, and that's really depending on what sort of biomass you use to make biochar. Why is that important? Why do you have such a large range? Well, it depends on the quality and the features of the biochar that you want to create, so depending on what you start with, and I'll come to that a little bit more later on. With enhanced mineral weathering, it's much about where the mineral fines come from and how far you've transported them, because they're obviously dense and more difficult to move around. So we're at the current time, sort of approaching December this year, we have the science and engineering report complete, and the design plan for the pilot projects emerging at the moment. We are looking at a live infrastructure project for the demonstration in a pilot scale. We're also going to have a reference site, which is a permanent, if you like, experimental site where our knowledge and expectations can be validated in detail over the long term. The funding that's associated with that is sufficient for quite a large scale project, in relative terms at least. And the requirement, and this is really the minimum, is 300 tonnes of CO2 removal, 1,000 tonnes of CO2 removal per year by the end of the project, which really means 300 tonnes of biochar and potentially 2,000 tonnes of dolerite. So we're looking at how we might incorporate that into a relatively small roads project, which is a bypass project in the southwest of England. When we look at what's required down the line by 2030, the 50,000 tonnes, then you have to have a very clear way of rolling this out across projects. So I suppose one of the things we're interested in at the moment in the context of this forum is how this technology might fit within rail infrastructure creation, and to seek particular stakeholders with whom to engage around that. In terms of the technical feasibility, I just want to sort of say a few things about both of them. With biochar, I said already that the properties of the biochar depend on what you start with. And if you want particular properties that are valuable, you may invest more in the material and select a particular type of feedstock. And I think if you start with wood chip, you sort of create any sort of potential functions that you might want. If you're going to start with something that's essentially a waste, then you're somewhat limited in the characteristics that you can create. I think in terms of the logistics, we have to think about how this might be done. Now, linear infrastructure is quite different from other engineering projects, I think, and you could, on a large infrastructure project, create the facility to make biochar material at a project level, and distributed across a linear construction site. And that's probably the way you would organise this for a large project. For the pilot project that we're considering, which is really, well, because it's a pilot project, is like sort of a commercial demonstration, we're likely to procure biochar directly from a producer. And at the moment, that's quite difficult to do on a much larger scale because that industry doesn't exist, but it's one that will emerge as the demand for carbon removal increases. And I think the cost of this is very dependent on the scale. Maybe that's obvious already, but also the logistics of how this is organised spatially. Yeah, but really, it's about designing this into landscape where it provides useful function. You can almost manipulate the landscaping and vegetation characteristics by how you design the soils that are integrated into the project. So it may be earthworks and potentially the roadside verge. Regulation is an important area here because I mean, I think there's two things really about getting this integrated into projects in a more general way. One is to establish a regulatory position with environment agencies so it becomes easier, and the other is to embed it within design principles or design practice. So the design manual for roads and bridges is probably where we want to get these materials specified in the longer term. With dolerite, I think I already said that, well, how far you transport has a big impact on the net carbon benefit, even though transport is relatively, well, it's not a big part of the carbon emissions, but if you start transporting it very long distances, it becomes more important. And quarries where dolerite as a specific mineral is generated are not homogeneously distributed across the country. They tend to be predominantly in the north and in Scotland. Fortunately, there's some in the southwest, which is a bit closer to where we're planning our pilot project. But yes, it's the cost as well as the carbon benefit is dependent on exactly where this comes from. But again, a little bit like the biochar, it's all about integrating this within the earthworks, the verges and landscaping around the project. But it does have potential as a fill material. We've had to look at quite a few risks, and I think there's been sort of a focus really in the science and engineering considerations. So we've looked at material costs and what might happen to those, and whether these are major, whether these are red, amber, or green risks. How important that risk might be. But yeah, regulations of planning and the dialogue with the environment agency has been quite important, and in fact also with DEFRA. Yeah, and I think I think there was a little sort of mention about this. Where is policy going to drive this? What's going to be the policy for? I think it is now national highways in terms of requiring emissions associated, embedded emissions associated with infrastructure to be addressed within the design. Pyrolysis as a means of producing biochar generates heat, so the carbon benefit is much greater if you have a use for the heat that's generated in the process of making biochar, which you need to think about that in the context of logistics and siting. Dolerite, on the other hand, is already stockpiled and potentially available at existing quarries, and the potential to scale up that utilisation is quite considerable. The regulation for dolerite is relatively simple because it is already used in the management of agricultural land, so it has an existing market and use, and it's much more complicated for biochar. At the moment, if you use a heating process to treat biomass, what you produce is automatically a waste, regardless of whether what you started with is a waste or not. So there is some existing regulation from the Environment Agency through the Low Risk Waste Protocol, but this is quite restrictive in terms of the scale at which you can operate. And at the moment there are proposals, well, there are voluntary standards and proposed publicly available standards for biochar which could be adopted, and I think that's aided by the existence of the EU fertilising products regulation, where biochar has already, or a specification for biochar has already been agreed at EU level, but it turns out actually the UK is not going to be immediately adopting that regulation, but coming up with its own specifications, fertilising products post-Brexit. So yes, I think the regulation is a potential barrier, and it's one that we're sort of amongst other of the current projects addressing with Environment Agency and DEFRA at the moment. That was a brief outline of the sort of the technical side of it, and yeah, happy to have any questions and hear comments that you might have. Thank you.
Already see a sea of hands, so if you can introduce yourself.
Hello, Arcadis. Just to ask, so when Ricardo gets sequestered door and sort of taken away, how do you measure the effectiveness of it?
Yeah, so I think this is ultimately the key challenge with enhanced mineral weathering. I think the answer is you can't. You can only do this really by extrapolation from very closely monitored and observed experimental situations. And I think when you define carbon removal on a site basis, it's very problematic because you know that almost by definition that those weathering products are going to move off-site. So there are ways that we can measure this experimentally within a contained site, but it's not something that you can really go and monitor on a site-by-site basis. But I think generally with carbon storage on land, I really think you want to avoid having to do anything that's site-based, really because the cost of monitoring becomes the dominant cost relative to the cost of the materials. So I think it's coming up with very good underpinning data to show the effectiveness of the technology and robust models that enable you to predict the effect, rather than worrying too much about the ability to go and measure it. But getting that data is quite critical.
I see a question here, but before we go to you, we have an online question.
Yeah, sorry, I think it's more of a clarification than a question. Daniel Pike, who's online, was asking, is he right in thinking that biochar is essentially burying carbon back in the ground? He says that it's burying coal back in the ground, but admits that he knows he's paraphrasing. But is that fair assessment? Or?
Yeah, I mean, I think so I suppose you could say that if you do carbon capture and storage, you're taking CO2 that was in coal or oil or gas and putting it back in geological storage underground. This is a little bit different in the sense that it's the plants that have, the vegetation that's removed the carbon. And that, but yes, you are you're storing it in the soil where the plants grew. That's right. Yeah. It's also recycling nutrients in the process.
Hello, so I've got a question. We use amine-based systems to capture carbon, actually, in other applications. How does this compare to technology versus traditional amine-based systems?
Yeah, I think it's. I think there's some additional benefits to be gained from manipulating land. So, in other words, manipulating might sound bad, but I think you can change the properties of the land around infrastructure in a way that might be positive, might have a value. So you gain some value from changing the soil. So it's not just a cost. Then on the other hand, there are these issues about certainty, and they're about also about longevity. So biochar won't last as long as geologically stored CO2, etc., etc. So really, it's possibly thinking about these technologies as something that can be deployed incrementally, but quite soon, rather than relying on other technologies which might be more relevant in the longer term, but maybe more difficult to get started soon enough. That's what I think.
We have a last question here.
Tom Wilson, WSP. You might already have thought about this, but one of the railway applications you would have for the enhanced mineral weathering would be the substitution of sand in the sand blanket that the railway track engineer uses with his ballast layer. Mm-hmm. You substitute the sand with crushed dolomite, and crushed dolomite is something that we have an embarrassment of in Scotland, since we've got most of the dolomite quarries within 30 miles of this very auditorium. Mm. And you could actually use the removed dolomite from ballast cleaning operations, screen that to get rid of the fines, and then crush the dolomite to get your crushed dolomite medium, and then put that back in the track as a capping layer. Is that something you're working with Network Rail to make happen in the future?
No, we're not, but I think it's a good angle. And as I said, we I think because the immediate opportunities that emerged were in roads projects, the engagement in rail has sort of paused, but I think we'd like to get it started again, and I think that's a good avenue to follow. I think what I would say, and yeah, you're right, there's a lot of dolerite there, and there's different ways you could incorporate it into a project. I didn't really talk about it too much, but the concentration of CO2 in the soil is very high where you've got vegetation. And that's important because then the rate at which CO2 is removed is much higher using these materials, because you can use up all those weathering products. Now, I think if you put it in a situation where there's no vegetation at all, the concentration of CO2 is going to be very similar to how it is in the atmosphere. And that means the potential to remove CO2 is probably a lot lower or a lot slower. So that's the only thing that I would say you would probably have to think about. The relative merits, because that doesn't really mean that the CO2 won't be removed, it just means it'll be removed over a longer period of time. But yes, thank you for that. I think it's a really useful suggestion.
Well, thank you very much. Thank you. Please share your appreciation. So we have come to the end. Right, we have closing remarks. Dan, do you have any closing remarks? Oh, I actually want to make that as well.
Thank you to our speakers. We're going to just run 2 minutes at a time, and I know loads of people have taxis, but so I'm not going to hold you. But one round of applause for everybody who's spoken again today.
Oh wow, that was very swift. Okay, so just